welcome. Thank you for the invitation and introduction. So I noticed that the introduction gets longer if I get older, so sometime better to retire. Okay. The notion of the essential dimension was introduced in the 90s by three people, Bühler, Reichstein, and Serre. So let me just first describe what it means informally. So suppose we have a class of algebraic structures or algebraic objects. So algebraic structures of some type, say of type A. Well, we will have plenty examples later, but those could be quadratic forms of given dimension or algebras with some properties, algebraic varieties even. So some algebraic structures of type A. And the idea is to estimate the complexity of this structure by assigning an integer, non-negative integer to this structure. Very simple invariant, just one integer should describe the complexity of that. This number is called the essential dimension of the structure. Just non-negative integer. So how can we use this integer? Suppose we have some other structure, say algebraic structure of type B. So we can define another integer, the essential dimension of B, and then we assume that these structures are related by a map from structure A to structure B. And the property we would like to have for the essential dimension is the following. Suppose that this map is surjective. So every structure of type B comes from some structure of type A. In this case, we will have the inequality. The first structure is more complex than the second one. Well, now a typical situation is that we work with the structure type B, and we would like to classify the structure of type B. Classify B. Well, you want to classify some objects, you just make a list of all possible objects. And this list is the classification of the objects. And suppose this type A structure gives this list of all possible structures which appear for B. And of course, the classification is complete if you have a map surjective. So every object of type B comes from the list. In this case, the essential dimension of the list should be at least the essential dimension of B. Well, you know, typically classification problems are very difficult, and before starting the classification, you can actually estimate the complexity by computing those numbers. You compute the essential dimension of B, you compute the essential dimension of A, and you check whether this inequality holds. If it holds, then, well, maybe there is a hope that the conjecture is true, that B is classified by A, but if this inequality fails, then for sure this classification is wrong. So there is no surjective map from type A structure to type B structure. So this is one of the applications of the essential dimension to destroy some conjectural classification theorems. Okay, now I would like to give some ideas how to define those numbers. Well, let me do the first example. We look at the quadratic forms of dimension n. Quadratic forms of dimension n. Well, quadratic form is a homogeneous polynomial in n variables. It can be written in this form: aij, xi, xj. Xi, xj variables, and aij are the coefficients. Well, for technical reason, it is convenient to choose a base field f which can be, well, any field. In particular, it can be field of complex numbers. It's a possibility. And then we consider the objects over, not only over C, because over the complex numbers we know how all quadratic forms look like, but instead we consider quadratic forms over all field extensions of F, including, of course, those that are not algebraically closed, some infinite extensions. So we look at quadratic forms over all field extensions, say K over F. So the coefficients are in K. And how many coefficients can we take? It's sufficient to take n square coefficients, but we also know that we can make them symmetric. So roughly n square over 2. Can we improve this number? Well, we consider quadratic forms up to isomorphism in that example. Well, there's a theorem. So at least in characteristic different from 2, every quadratic form can be diagonalized. So it is isomorphic to the quadratic form of the shape b1, well, some other variables v1 squared, b2 y2 squared, bn yn squared, with the bi's in the field. So it is sufficient just to take only n parameters to give a quadratic form. So we can say that the essential dimension, the complexity of this class of objects is at most n. And it turns out that you cannot do better than that. So the essential dimension of this class of objects is equal to n. Okay, how can we describe this number n? We can look at this subfield between f and k generated by the coefficients b1, b2, bn. And the quadratic form is defined over this smaller field because the coefficients belong to this smaller field. So the original form turns out to be defined over smaller field. So how can we estimate the complexity of this field? Well, you know that if b1, b2, bn are algebraically independent, then the transcendence degree of that field over f is exactly n. But they may not be algebraically independent, so transcendence degree of this field over f is at most n in any case. So it turns out that quadratic form Q is defined over a subfield of K of the transcendence degree at most n. So the question is how many algebraically independent parameters you need, the smallest, to define the structure. Well, one more example before I give the precise definition. Second, we look at matrices over a field K, n by n is fixed, and modulo the similarity relation, given by conjugation. The two matrices are similar if each of them is the conjugate of the other for some invertible C. It is the same as the set of all operators on the vector space of dimension n up to isomorphism. What is the essential dimension of this set? Well, of course, to give a matrix, it is sufficient to give n square parameters, but we do matrices over some equivalence relation, so maybe we can have less than that number of parameters. In fact, we can do better than that. If you recall the rational canonical form, every matrix is similar to a matrix in the rational canonical form, which is the block diagonal matrix consisting of the matrices of this form. One below the diagonal, then anything in the last column, and 0 everywhere else. So every such block is given by that many parameters equal to the size of the matrix. So the essential dimension in this case is at most n. Essential dimension is at most n. In fact, it is equal to n, which we will see very soon after I give the definition of the essential dimension. So we are looking for the smallest number of parameters which can describe the object, algebraically independent parameters. Okay, here is the definition. First of all, we need to understand what algebraic structure means of given type. As I said, we have field f fixed, and we consider all field extensions of f, k. To give an algebraic structure is the following. You give a set for any field extension k. A of k, just a set. In the first example, it was the set of isomorphism classes of quadratic forms over k. In that case, it is that set of matrices modular similarity relation. And we have field extension operation. If you have a larger field k prime over k, still extension over f, we are given a map. From a of k to a of k prime. Well, in fact, one should also require that the composition of such maps is equal to the map for the larger field extension. And if you look at this definition closely, A is nothing but a functor from the category of field extensions of F to the category of sets. But sometimes we will call such a structure a functor. Sometimes we say that A is an algebraic structure. So very formal construction. Now we pick a field extension K over F and every element in that set, A of K. So we just pick either quadratic form or matrix n by n in our examples. Well, A is defined over the field, large field K. We will look at smaller field over which A is defined. So we take a subfield between F and K, say L. And we say that A is defined over L if there exists a B in A over the smaller field L such that B goes to A when you apply the map from A of L to A of K. So A can be defined over a smaller field. Then we look at the transcendence degree of the field of definition L over F and take the minimum of these numbers over all fields of definitions, over all fields such that A is defined over L. And you call this number the essential dimension of A. So every single structure has the essential dimension, the transcendence degree, the smallest number of algebraically independent elements generating the field, is the essential dimension of A. And finally, the essential dimension of the structure is the maximum of the essential dimension of the single object A for all field extension K over F and all A of the structure over K. So this is the essential dimension of the structure. Okay, this is the definition, and there are simple properties. The first property is, as I said, that when A is surjects on B, which means that for every field A of K surjects on B of K, then the essential dimension of A is at least the essential dimension of B. That immediately follows from the definition. Okay. The second example, rather property, well, the second is an example. Look at the variety, X over F, algebraic variety. You can view X as a structure as follows. You write for X of K, for the set of points of K over over K. So if X is given by a system of algebraic polynomial equations, then X of K is a set of solutions of those equations. So every variety has points over a given field. And of course, if K prime is a field extension of K, then solutions over smaller field are embedded in the solutions over larger field. So these maps in the definition are just inclusions, injective maps. And then we can ask what the essential dimension of X is. And again, it's fairly easy, follows from the definition that it is nothing but the usual dimension of the variety. Okay, now I would like to go back to the example 2. In that example, we know that The essential dimension is at most n because every matrix is of this shape up to similarity relation. But I would like to prove the other inequality, the opposite inequality. What I do, I construct a map from our structure to k to the n, to the tuples of elements over the field k, which is, by the way, the k points of the affine space. An is the affine space, and k points are just tuples and tuples of field of k. What is this map? You take a matrix A to the coefficients of the characteristic polynomial. The characteristic polynomial is invariant under this equivalence, so you can really, you have this map well defined. The coefficients of the characteristic polynomial of the matrix. And this map is surjective because obviously for any coefficients of the characteristic polynomial you can find a matrix with that polynomial. And when you apply 1 and 2, you see that the essential dimension of our structure is at least the essential dimension of the affine space, but it's a variety of dimension n. Dimension of an is n. So we get the opposite inequality, and so the essential dimension is equal to n. So very often, maybe in most of the cases, the problem of determining the essential dimension splits into two problems: to find the upper bound for the essential dimension and to find the lower bound. And the methods are very different. And if you're lucky, then your bounds match, and then you get the precise value of the essential dimension. Already in that example, you see relations of the essential dimension to algebraic geometry. And in fact, there are many connections between this notion of essential dimension with many areas of algebra. Now I will do algebraic group part of my talk, but there are also relations to Galois homology, to algebraic cycles, and to evaluation theory. Nearly every part of algebra somehow intersects with the notion of the essential dimension. Well, let's take an algebraic group. So it's just a variety and a group at the same time. So the groups given by polynomial equations. And I would like to define the notion of a torsor for the group G. Well, it is maybe easier to explain as follows. Suppose that G acts on a variety, algebraic variety, capital X, freely. Well, without fixed points. Unfortunately, in algebraic geometry, it's not sufficient to construct the factor variety. X mod G may not exist. But if X mod G exists, the canonical map from X to the variety of orbits is called a G-torsor. So it is a gadget, it's a morphism so that G acts on the fibers of these morphism in a nice way, without stabilizer and transitively. Well, sometimes the base variety for a torsor just one point. So such torsors we will call torsors over K. So x to the point is a G torsor over K, over F. So in that case, G acts on X simply transitively. Well, here is an example of such true torsors. It's a basic example. First of all, G is the automorphism group of some object, say A. A is an algebraic object, whatever that means. Could be a matrix, quadratic form, algebra, and so on. Algebraic object. Suppose you have another algebraic object, B, and you have the operation of the change of the base field. So we say that B is a twisted form of A if B, when you lift the base field to a larger field, say K, is isomorphic to A over K for some field extension K over F. For example, two quadratic forms may not be isomorphic over given field, but they become isomorphic, say, over larger field. And in this case, we say that one is the twisted form of the other. If you have such a B, you can form the variety of isomorphisms between B and A. And G acts on X, well, nicely, simply transitively. Because you can, for every isomorphism between B and A, you can compose it with the automorphism of A with an element of G. And conversely, every two isomorphisms differ by unique automorphism of A. So X is a G torsor over F. So we have a map from twisted forms of A to G torsors over F. It takes B to the variety of isomorphisms between B and A. And I would like to list some of the examples of this nice correspondence, which is, by the way, very often is a bijection. Well, examples. First, PJLN. Well, it's a projective general linear group, modular the center, the subgroup of scalar matrices. It is the automorphism group of the matrix algebra. Every automorphism group of the matrix algebra is given by conjugation, by an invertible matrix. Therefore, PJLN torsors are the same as under the correspondence with the twisted forms of the matrix algebra, and the twisted forms of the matrix algebra are exactly the central simple algebra. Central simple algebra over F of dimension n squared, or degree n, the same as degree n. Degree is the square root of the dimension. Well, second example, the symmetric group Sn, the finite group, is the automorphism group of the algebra f to the n. It's f cross f with itself n times by permuting the components. And then Sn torsors the same as the twisted forms of Fn. So all algebras which become products of n copies of the field when you extend the base field. And those are known as étale algebras, étale F algebras of dimension n. Well, the main point is that for many interesting objects like this and many others, quadratic forms and so on, the objects are in one-to-one correspondence with the torsors for some group G, namely for the automorphism group of the object. This applies to the objects with big automorphism groups. Well, you fix a group G and you consider the following structure: A of K, just the set of isomorphism classes of G torsors over K. And then you can ask what the essential dimension of this, and the essential dimension of this A is denoted by the essential dimension of G and is called the essential dimension of the group G. So by definition, the essential dimension of the group G is the essential dimension of the class of the torsors. It's complexity of the class of the torsors. Essential dimension of PGLN is the complexity of the central simple algebras. Essential dimension of Sn is the complexity of the F algebras. Well, I would like to look at that example because, well, it's certainly a very simple object, but we don't know the essential dimension of Sn. What is an étale algebra of degree n? In fact, at least the base field is infinite. We can write such an algebra as the factor algebra, well, say over K. So it's factor algebra of the polynomial algebra in one variable by ideal generated by a polynomial of degree n. So F monic of degree n. Polynomial over K. Well, how many parameters do you need to give such an algebra? Of course, it's sufficient to give the coefficients of F. polynomial f is t to the n plus a1 tn minus 1 plus so on an minus 1t plus an. So we have n coefficients, so the essential dimension is at most n. The essential dimension of the symmetric group is at most n. But we can do better. We can change the variable and can simplify the polynomial. We only consider algebras of this form, but you can change the generator to the other generator, then the polynomial changes. And everyone knows how to simplify the polynomial. You can, replacing t by t minus something, you can kill a1. Okay? So we see that essential dimension of Sn is at most n minus 1. Well, of course, if n is greater than, it is at least 2. But you can do better. You can scale the variable t, and you can make these two guys equal by multiplying t with some constant. So we see that the essential dimension of Sn is at most n minus 2 if n is at least 3. And in fact, you can do another trick to see that the essential dimension of Sn is at most n minus 3 if n is at least 5. On the other hand, we have a lower bound that the essential dimension is always at least the integral part of n plus 1 over 2. So here is the list of values of the essential dimension which are known. That is n, and here is the essential dimension of the symmetric group Sn. One, it is 0. For 2, when you have the quadratic polynomial, you can eliminate the linear term. 1. For 3, it is 1. For 4, it is 2. 5, 2. 6, 3. 7, 4. Okay. And for the other values, it's still unknown. Open problem, very interesting. So basically what you need to do, you need to change a variable, change the generator of the algebra, this element represented by the variable t, to make the coefficients of the polynomial algebraically dependent as much as possible, so that they generate the field of the smallest possible transcendence degree. And so you can reduce by 3. And there is no even conjecture. There is no natural number between these two numbers, n minus 3, say, and this one. So it's hard to say what the actual conjectural number is. So it's still open and very interesting problem. I would like to mention another problem. About the essential dimension of the group PGLN. So it's a complexity of central simple algebras of degree n. Well, no one knows how central simple algebras look like. And let me give you a very special class of central simple algebras. You assume that primitive root of unity is in the ground field, and you pick two elements, A and B, in the ground field. Well, if you pick an extension, K over F, you take A, B, non-zero elements in that field, K. And you construct an algebra. I write A, B, N, generated by two elements, x and y, non-commuting elements, which are subject to the following relations. X to the n is a, y to the n is b, and then yx is equal to psi xy. Well, such an algebra is called a cyclic algebra. Cyclic algebra over k of degree n. Well, I think everyone recognizes the classical quaternion algebra, -1, 2 over the reals. This is the classical quaternion algebra, and it is an example of a cyclic algebra. It is a central simple algebra of degree n over k. Well, one can ask whether every algebra of degree n over k is a cyclic algebra. And the answer is no. If n is a composite number, not a prime, there are examples of other algebras. But it's still an open question. It's conjecture or a question. If n is prime, is any central simple algebra of degree n cyclic? The answer is yes. If n is 2 or 3, and it's open for n at least 5. Okay, and I wouldn't be very surprised if someone would show a counterexample to this problem by establishing the inequality that the essential dimension of PGLN for such n is at least 3. If this happens, then the answer is no. Why? Because it's exactly the classification problem. The number of parameters needed to describe a cyclic algebra is 2. You need just A and B only. If essential dimension is at least 3, then not every central simple algebra is given by the cyclic algebra. So just started my lecture with representing the two classes, the class we want to classify, and it's the class of all central simple algebras of degree n, and the list. Now the list consists of cyclic algebras. The essential dimension of the list is equal to 2. If the essential dimension of the class is at least 3, then there is no surjection. The map is not surjective, so not every algebra is cyclic. Well, this is obviously a hard problem, and we don't know calculation of the essential dimension for many values, only for some small ones, for 2, 3, and 4. There is a variant of the essential dimension which is somehow simpler to compute. It's called the p dimension. We fix a prime p, and then we ignore all the effects of the degree prime to p. We define the essential dimension of a structure A with respect to this p, or essential p dimension, as the minimum of the essential dimension of the class A, but considered over field extensions k over f, with the property that k over f is finite, and this number is prime to p. So in other words, we concentrate on just one prime p. In this case, we can see that the essential dimension of the class of central simple algebras of degree p, which is the same as the essential dimension, of course, of PGL p, is equal to 2. Because, well, it turns out that the following is true. If you take any central simple algebra of prime degree, P, over some field, I'll say F, we don't know whether it's cyclic, but what we do know that there exists an extension K over F of degree prime to P, such that if you extend the algebra to that field, it is cyclic. And since we kill the effect prime to P, then you can say that you need just the two parameters, A and B, to give any algebra of prime degree. What happens for the other degrees? Well, degree should be a power of a prime if you look at the p dimension. So now you look at the central simple algebras of degree p squared over k. Well, such algebras of degree p squared contain algebras which can be made from cyclic algebras, the tensor product of cyclic algebras. These guys contain A, B, the tensor product with CD of two cyclic algebras. And then you can ask whether every algebra in this class is of this form. Well, it has been known, of course, for a long time that the answer is negative, but the conceptual proof would be to calculate the essential dimension of this class. And it turns out that the essential dimension of p dimension of this class, which is the same as essential dimension of PGL p squared, is equal to p squared plus 1. It's much more than 4, even when p is 2. It is bigger than 4. And that means that not every algebra of degree p squared is of this form. So actually this statement shows that the algebras of degree p squared are much more complicated than we think. The number of parameters you need is p squared plus 1. Okay, we can modify the problem by also introducing some restrictions not only on the degree of the algebra, but on the exponent of the algebra. So let me define the exponent. If A is the central simple algebra over field F, then you can take the tensor product of A with itself. And it turns out that for some number of algebras, say E, you will get a matrix algebra of some order over F. And this E, the smallest number E, is the exponent of the algebra. Well, if you still look at the algebras of degree p squared, then the exponent of this algebra can be either 1, in this case the algebra is the matrix algebra itself, or p squared. There are 3 possibilities. we can look at the essential dimension of the class of central simple algebras of exponent p. So let me write as CSA p squared comma p for the algebras of degree p squared and exponent p. So if you just simply take all the algebras of exponent of degree p squared, we get the essential dimension p squared plus 1. If you look at the algebras of degree p squared and exponent p, well, the answer is interesting. It looks like this should be smaller number because it is just the subclass. We only look at algebras of exponent p, while here we look at all the algebras. But the answer is, it is indeed smaller than this number 4 if p is 2, and it is p squared plus p if p is odd prime. So this is a result by Bach and myself. So for p equals 2, it is smaller than this number, but for other p's it's even bigger. So the complexity of algebras with prescribed exponent turns out to be larger than essential dimension of all algebras. And there is an explanation of this fact. If p is 2, every algebra in the class of algebras of degree 4 exponent 2 consists of tensor product of two cyclic algebras of degree 2 now. And those are called the quaternion algebras. And this is the classical theorem by Albert, that every algebra of degree 4 exponent 2 is a tensor product of two quaternion algebras. So we do need 4 parameters a, b, c, d to give such an algebra, and exactly why the essential dimension of this class is 4. The essential dimension of the class of all algebras of degree 4 is 5. So there are algebras not of this form, which simply says there are algebras of exponent 4. But when p is odd, of course p squared plus p is greater than 4. And again, we see that even in the class of algebras of exponent p, not every algebra is of this form. Not every algebra A in the class of central simple algebras p squared p is AB times CD. So again, we use the essential dimension to disprove a conjecture, and in fact you have some estimate that it's really a much bigger number. So it probably shows that the algebras of degree p squared exponent p are much more complicated than the algebras given by just the tensor product of two algebras. Maybe I will give you one last example. It's about quadratic forms. The class is quadratic forms of trivial degree of even degree to n, even dimension to n, trivial discriminant, and trivial Clifford algebra and split Clifford algebra. Well, I have no time to explain what it is. I just want to show what the calculation of the essential dimension gives us. Essential dimension depends on the of degree. Now, let me write n, but n is even. So it turns out that we can precisely compute the value of the essential dimension. It is done by Reichstein. Brosnan-Vistoli. Chernousov and myself. Well, I will again write a table. And here's the essential dimension of this class, depending only on n. One can show that there is only one form in this class of dimension up to 6. When n is up to 6, there is only one form, so it's just essential dimension is 0. When dimension is 8, well, quadratic forms of this type also are classified. And here is the general quadratic form of dimension 8 with these properties. This is a form AB, x squared plus by squared for short. A1C, 1D, the tensor product of these forms. It's called the Pfister form, and it's multiple Pfister form. So you count the number of parameters, you see it says 4. For 10, it is also 4. For 12, it is 6. For 14, it is 7. In fact, all quadratic forms with such properties of degree at most 14 were classified. And classification approximately of this type for each of these degree. And that's how we easily compute those numbers. And what happens after that is quite interesting. For degree 16, where in fact we don't expect any reasonable classification of such forms, the essential dimension already jumps up to 23. And if you look at 18, it is 104. And in fact, this value is approximately 2 to the n over 2 minus 1. So it's exponential, which you don't see when you look at the short part of this list. And the explanation of that in this range, we have the classification result, which simply lists all these guys. Later, we don't have any reasonable classification, and probably such a classification doesn't exist, and then the essential dimension goes up exponentially. So it's an example of this phenomenon when the essential dimension can predict or at least explain some classification results in algebra. Okay, thank you.